LNG, and oil and gas, and all these LNG offshore and onshore. So here definitely these projects will have to go through different stages. The major milestone, different stages of these projects are basically engineering and procurement and construction. So engineering phase will be just like it will be a basic engineering and detail engineering, in which the the basic philosophies and design bases and specification data sheets are being prepared, which are required for the basic engineering and detail engineering. Definitely then after that one we will go to the next phase, that is procurement of all the equipment required for that particular project. And then we will make the material acquisition RFQs, and we will float the inquiries, we will get the offers, and we will do the technical bid evaluation, and then we will do the next third phase, engineering for construction. Engineering for construction definitely deals with the required documents and drawings for the construction engineers. So these are the different important phases of any UPC project. So in these during course of actions, definitely we'll come across the P&IDs. So we will talk about that one next half an hour. Before that one, I would like to give a brief introduction about the UPC, and there we will see where the process flow diagrams and P&IDs stands, and then we can focus on the P&IDs. Is it okay? You can hear, no? Hello? Hello? Is it audible? Hello? 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 Agenda. Today's agenda will be on the following topics. First, we will have an introduction to EPC project management. Definitely, when any project is done, then we should have a management schedule and management program. And the next phase will be the project management workflow. What are the different phases of workflow? And then engineering document issuance purposes. What are the different documents or drawings and their issuances and their purposes? At different stages, what are the purposes and what are their aspects. And of course engineering workflow and procurement workflow will be through different phases of that one. And then next thing, which will be the important thing, is schedule, which will be monitored by the project control. And the schedule dependency will depend upon the time frame, and of course the the complete level 4, level 1, level 3, level 4 is project schedule, and the upfront concepts which will be required for the construction people. So when we talk about the aspects of EPC project, there are as I said, three different phases: engineering, procurement, and construction. So if any company or client would like to make a plant of oil and gas or LNG, LPG, or onshore or offshore of any type of industry, they would like to start with that one. Then they will first do the basic engineering, they will do the front end engineering design feed, and then they will call a contractor, and then they will put an inquiry, and then they will get the quotations from the contractor for the EPC projects. So the awarded contractor will then start designing and making the documents for procurement and making the deliverables or documents or drawings for the construction purpose, so that a construction engineer at the site will use those one. The basic aim is to construct a plant, but it has got different phases. So when we talk about the different phases and its management, so here, as I said, the EPC phases will have the first phase is the feed, front end engineering and design phase, which is nothing but a basic engineering design which will be used during the detail engineering phase. So what is feed? Feed is generally a separate package covering different positions of the project. It will be a brief study and feasibility study about the plot plan, whether the required space is sufficient, whether the required budget is sufficient, and whether the required schedule is sufficient for the complete management of that particular project. So this is the most important aspect of any project. So in the beginning, the front end engineering or basic engineering is done before starting to are going ahead to detail engineering. So under the CPC contract, the contractor designs completely the installation and procures installation required documents, and then makes the necessary arrangements to procure all the equipment or materials required for construction. So this is about the management. Definitely in this one, there will be a schedule, and that schedule will be monitored at these different stages. And there are different milestones set, and those milestones we will see what are those milestones afterwards. But before that one, if you talk about the project management, then broadly we can say we can just segregate into three different categories: EPCM, EPCI, EPIC. Definitely, these are not having much more different, but slight differences are there. And if you talk about engineering procurement and construction management, and this is nothing but the EPC management, and this type of contract is different than EPC contract, is that contract is not directly involved. So EPC management, EPCM will not directly involve into that one, but definitely they will be doing the complete monitoring of the project, and the construction also they will manage. So they will do the complete administration till the construction. And when we talk about EPCI, then here engineering, procurement, construction, and installation also. So here after installation, after construction, then definitely installation is required. So in this phase of project management, installation is also monitored. So as opposed to EPC contract, the offshore facility or onshore facility or vessel that is constructed has to be transported, installed at the project. So here, not only the engineering phase, not only the procurement and construction phase, but of course the installation or erection will be done. The next phase will be left is nothing but the commissioning actually. So here, apart from engineering, procurement, and installation, the commissioning phase is also added, APIC. So generally, this is the full phase of the contract, which will be given to the contractor, so that they can do the complete all these three phases, and we call it as lump sum turnkey contract. So definitely in this case, the client will just come and turn the key so that the complete project will be started. So it is a wholesale responsibility of the EPC, EPIC contractor to do all these phases, to do the basic engineering, to do detailing, to do the detail engineering, to do the engineering for procurement, and to do the engineering of installation, and make the drawings and all those things, so that an installation or site contractor or an engineer can make use of those things. And then next phase will be the commissioning. Commissioning is nothing but you have to just start with the first fluid, and then you have to do the complete arrangement, close some walls and start some walls. And then first time you have to take the float, you have to take the fuel, and all those precautions you have to do. So the commissioning is the most important aspect, which will be the last phase of a contractor before handing over to the client. So these are the different project management phases, we can say: EPCM, EPCI, EPIC. Here, these are the life cycles. As I said, basic engineering and detail engineering is a engineering phase where we make the complete design philosophy, design basis, data sheets, and other like instrument index or PMS and all those things, P&IDs and process flow diagrams. And next phase will be the procurement. So here we need the data sheets and material requisitions or RFQs, so that the inquiries can be floated and given to the vendors, and the vendor offers will be received, and then those will be reviewed, or technical bid evaluation will be done, and then commercial bid evaluation will be done, and we will see which vendors are suitable for that particular equipment, or for that equipment, for that particular part of the vessel, or maybe the equipment or item. Then PO will be given. Once the PO is given, when the PO is given, then the vendor or contractor or the manufacturer will start manufacturing, and they will start giving the vendor documents, and then those are approved, and then the items will be sent to the site, and the construction phase starts. So site erection, commissioning, and for will be done, and finally the performance management. So these are the different phases which we told in the three phases previously. So next, when you talk about the organization, so you definitely have to have an organization for these complete EPC projects. So in this one we will have a project manager and project engineering manager, and then different engineering team will be there, for example process engineers, and then system or package engineers, mechanical or piping engineers, civil and instrumentation engineers, and electrical engineers. And these are the complete engineering team which will be handled by project engineering manager under project management and the project control. The next phase will be the next factor of this one organization chart will be non-engineering. Non-engineering will be the management persons, those who will be monitoring the engineering phases and construction phases and procurement phases. Definitely, these are the project managers, project engineering managers, project controls, project coordinators, project administrators, and then project engineers, and a team for procurement, a team for complete making that automation or planning, and then quality control, administration of the complete project, and then accounting, of course, to have the finances to be controlled. Then last phase will be the construction. At site, we should have a site office and a field management, and the site contractors will be assigned or given the authority to do the construction. So engineering, all this team will be supporting to the construction team, and non-engineering department will be coordinating between these two groups. And if you talk about the same thing, like here it is shown in this style, engineering, procurement, and construction teams will be directly under project realization of project management, commissioning, and project control, quality control, and safety, HSSE, and project services. All these will be coming under project management. And when we talk about the engineering discipline, as I said, a project management or project manager under him, project engineering manager will be there for all these three phases, EPC phases. Here different disciplines will be there: instrumentation and control, and layout and piping will be handled by the piping or mechanical engineers. And here we can have the equipment or static or rotating, and then process and electrical. Process engineers definitely will do the complete required block flow diagram. They will make the plant, like they will be the first persons, those who will be making the process flow diagrams, and then it will be converted into P&IDs that we will talk in the next half an hour, how the process flow diagram and process engineer will make convert the process flow diagram into P&IDs, piping and instrumentation diagrams, which will be referred by everybody, especially by the piping department, by the instrumentation and other engineering teams. Of course, electrical team will be responsible for all the electrical equipment, for the data sheet of motors and all those in the equipment. Here comes the mechanical equipment, the static and rotating, and the civil engineers will start making the foundation and other things. And of course, HSE safety engineers will look after the fire hydrant and other fire and gas and other equipments. And of course, here instrumentation control also includes the telecom, CCTV, and PAGA. So these are the different engineering disciplines which are generally involved in the engineering phase and procurement and construction phases. So here workflow, if you talk about the engineering workflow, here, workflow concept is required to fully understand for someone who is involved in the EPC planning and activity sequencing. So when you are into the planning and all these schedules when you are making, then you will make the level 1, level 2, level 3, and level 4 schedules. And these are the schedules made in generally Primavera or any other relevant softwares. These softwares will give you level 1 to level 4. Level 1 is the basic, like only milestones, and level 2 will be little bit broader, and then level 3 and level 4 will be the detailed complete phases and detailed individual deliverables of individual disciplines with planned dates, and that will be controlled. So project schedule, project monitoring schedule, PMS we call it, will be monitored under this engineering workflow. So here, these level 4 schedules will be monitoring actually the complete engineering phases done by the different types of engineers. Like chemical engineers will be doing the process engineering, civil and construction engineers will be doing the civil and structural complete from data sheets to the architectural drawings and all those things, and mechanical engineers will be doing the static and rotating data sheets and making pumps and all rotating equipment or diesel generators or all the data sheets and all those engineering they will do. And piping engineers, both basically those are mechanical engineers, but they will be doing the only piping, and then piping stress analysis will be a different part of that one. And then, of course, electrical engineers will be doing the engineering, procurement, and construction phases, and they will be helping them in making the SLDs and other MCCs and motor data sheets and motor controls and interaction with instrumentation for the control from the DCS. And of course, instrumentation will take the P&IDs, and then they will start making the instrument index, IO list, and other different deliverables like specification for field instrument and other package instruments, and specifications for different instruments and data sheets for pressure gauges to pressure transmitter and all level transmitter pressure, all physical variable instruments, and they will make the data sheets and all those things. So they will do that type of engineering. And then, of course, general engineering will be nothing but actually project engineering management. And of course, HSE engineer will be doing the complete HSE aspects here. In this case, the fire and gas and mitigation and of fire, they will have the fire hydrants and foam and other uh, fire controls and HVLR and MVLR and all those things. They will be taking care of those engineering, and they will be the key aspect for the safety of the complete plant based on the material we are handling, or based on the hydrocarbon in LNG in oil and gas and in offshore and onshore project. The HS engineer plays a big role, because the fire and safety is very critical right now. So when we talk about the engineering flow, as I told, the complete piping routing diagrams will be made, and before that one, PFD, then P&IDs will be made. All these drawings will be issued in different uh, stages, and those are the stages will have their purposes. So any document issued by any discipline engineer, it can be mechanical, it can be civil or electrical or instrumentation, the documents or drawings will be issued with a purpose. The purpose will be issued for internal review, or issued for design, or issued for approval, or issued for construction. So we will see the different aspects of these workflows. But all these engineering workflows are path for construction. So our aim is to do the constructions. So whatever it may be, when we are doing basic engineering, when we are doing engineering, when you are doing engineering for procurement, the basic concept is to facilitate the construction at site people to have all these required drawings and data, so that they can go to the field, they can start making the plant and start making the construction. So the final phase of deliverables issuance will be issued for construction. So these are the final drawings which will be for that purpose issued. So here, if you see about documentation issuance discipline wise, like process will do any diagrams, and then geographical drawings will be the topographic survey and site survey, and other soil testing will be done by civil and construction. These are the major milestones. We can say calculations will be done by process and civil, and of course mechanical will also do the calculations for the static and rotating, and then equipment or material specification they will make. And then piping engineer will take the geographical drawings and layouts, and then they will do their own calculations, and they will make the specific data sheet for their piping material PMS. And then site work, of course, will be, so process will not, if you see in this one, piping, and after that one electrical will also make their diagram, SLDs, and their required drawings, and their MCC drawings, electrical drawings, and their data sheets for motors, and then all those procurement and construction drawings. They will make location layouts, and distribution, lighting, and other things. Instrumentation will make their instrument index, IO list, and all those drawings in these different phases. Of course, calculation is also covered by instrumentation for the control wall, sometimes will be done by process. And the equipment specification, material specification, and data sheets will be done by mechanical, piping, and electrical and instrumentation. And site works will be done by civil, mechanical, piping, and electrical instrumentation. If you see here, whole of this one process plays a big role. But in the beginning, once they make the PFD, then P&ID, then once they do the process flow diagrams and process calculations, heat mass balance, and all those things, they will hand over to the engineering team, and then their job will be finished, and those will be carried out, the means that will be carried forwarded by other discipline engineers. So these are the workflows, we can say, if we talk about the different uh, engineering disciplines. So this is just about the flow chart of engineering equipment. Engineering, this one project engineering manager will take the inputs, and then it will be given to the team, and then adequacy check will be done by the process, and then it will be identified if it is not adequate or not. Then we have to go back to the client and we have to say, hey guys, your plot plan or your equipment, whatever you want, cannot be accommodated in this schedule, in this budget, or in this plot plan. So that will be there, and then we will start preparing of documentation and then checking and all those things. That interdisciplinary check, once we have these phases, then definitely all these engineering disciplines will interact with each other. So once they interact with each other, then we call it as interdisciplinary checks. Any document when we are issuing, then needs to be checked by other relevant discipline engineers. For example, if a control room is being made just by civil engineer, then they have to send it to the instrumentation engineers. Or if a substation is designed by civil engineer, then it has to be referred by electrical engineer. They have to certify, they have to say that the construction, the after construction, of civil construction, the complete substation, whether it will be feasible to have my cabinets, the layouts and all those things, those rooms are adequate for all their equipment or not. So these are the interdisciplinary checks which are always required. And then the next phases will be adequacy check. Is once it is the IDC check, once it is done, then we can go to the release of the documents to the concerned departments, and then to their counterparts, to the clients. And then critical documents, of course, will be checked by instrumentation or electrical or piping or their respective HODs. Otherwise, the lead engineers and team will handle this one. So like that, the phases of these engineering execution will be done here. If you talk about execution in a broader way, input for engineering, and then if it say, for example, here there are two phases. One is the phase of engineering, and the other phase is phase different next phase of modeling. Nowadays it is more important because the visualization is much more important. And when you do only the engineering without visualization, then you can be in dark. You don't know what is the plot plan, and where the pipe rack is going, and where the trench is digged over there, and then maybe some pipe is coming over there. So when you develop a complete visualization, and it will be just give a clear cut picture, then we will have more idea. So that is the reason we go with 3D modeling. So 3D modeling is the next engineering phase, so engineering and designing. So nowadays the 3D modeling has got into deeper, and then 3D modeling is much more helpful into the designing and engineering phase, because it gives you clear picture whether the clashes are there, or whether the roads or the layouts are sufficient, whether the rooms are sufficient or not. And if you have to do the correction, then at the engineering phases only we can do. So 3D modeling, when we start this one, and then it will be reviewed by lead engineer of different disciplines, and then if the comments are there, we will go back. And then once it is done, 30% we will have. At the 30% stage, we will review internally and then review with client. And then any tags are taken. If, for example, it has to be moved here and there, that will be suggested by the client, and then we do it. Then we will extract 2D, and then we will give it to the client that, okay, these are the 2D drawings which are taken out from the 3D. And the next stage will be the 60%, the next phase of that one, modeling. And there also we'll do the much more corrections, and where by the time we will get the vendor drawings, and then we can have more clarity. So that will be the next phase of modeling. So 30% we will do the modeling, and then 60%, then the final stage will be the 90% model review. So at each stage we will have the 2D deliverable extracted, and then based on that one, any comments are there, and then once it is done, then design authority review will be done, and then finally it will be given to the client. And once the client approves, then we can say that when it is issued for construction. So once it's issued for construction, then the client will say, okay, I am approving it. So once it is approved, AFC is nothing but approved for construction. Once the client approves those documents, then these are ready to be taken out for the construction people. So these are the drawings. Or AFC document will be given in the hands of the construction team. So the construction engineers will go to the site, and they will start making the plant construction. In between, we can have material acquisition, technical bid evaluation, and then final acceptance test in the workshops, and for the equipment, for the major equipment. And of course, those things will be separately done. And once the AFC is done, then our engineering phase will be finished, and then the document will be archived. As I said correctly in earlier this one, the purpose of any document will have different prospects and different purpose at different stages. In the beginning, issued for review, issued for design, or issued for approval. Next stage will be issued for construction, or issued for procurement, and procurement support is done. So these phases will be having, for example, if it is production or any other phases, then if it goes to the production department, quality check will be done, and once it is done and IDC and quality acceptance, then definitely it will be ready for the manufacturing or fabrication. So these are the different engineering workflows which we can see here. Scope of work document will be studied in the beginning, and design basis or design philosophies will be prepared, or it will be given by the client when it is done in the basic engineering or front engineering. And if it is done in the front end engineering design phase and already basic engineering is done, then we can directly use those specification and design basis and design philosophies. But if it is not done, then we have to design and we have to make those things so that we can make use of that one. So these are the basis of our basic rules for our design engineering. So here the layouts will be done by the piping, and others will be supporting them. And then of course the process engineer will be making the process flow diagram and P&IDs. So this is the place where the P&IDs are coming, and those will be referred by other disciplines, like piping will be using, instrumentation will be using, electrical will be using the P&IDs, and further their engineering will proceed with there. So here a cable block diagram or other block diagrams will be prepared by the respective discipline. If talk about instrumentation, then they will take the P&IDs, piping layout and other layouts, and they will start making the block flow diagrams and cable block diagram, and they will do cable schedule and all those cable routing and all those things based on the 3D model, and all those things they will do. And of course these are the different stages, hook up and all those things. This is from the instrumentation perspective, just a view of that one. And then these are the cycles, as we said earlier. We have seen piping, civil, electrical, mechanical. These are the different phases. When these engineering teams will be doing these phases of engineering, then a project control will be monitoring that one. So when they do the monitoring, then they will have the rule of credit. The rules of credit will say that one, each level 4 deliverable will have the weightages for each deliverable. For example, if you are issuing plot plan, if you are using P&IDs, if you are using one layout, if you are making the 30% model, then it has got certain weightages or milestone. Those milestone or weightages will give you where do you stand when you are doing we are doing monitoring of the project. So with these weightages, or the progress will be monitored in this fashion. So each deliverable will have their weightages, and with this perspective we can have the complete cycle of the project monitored. So this is nothing but for monitoring purpose. Now we'll talk about the process of chemical engineer. What do they do here? They make the process flow diagrams with the help of heat mass balance. They do the calculations, heat mass balance and all those things, and thus PFDs will be shown to the client. And then with the help of the PFDs, they will develop the P&IDs, piping and instrumentation diagrams. Those are the inputs for other disciplines. So these are the inputs for rotating pressure vessels, like static engineers who will be making the pressure vessels, heat exchangers, and then fired equipments, or any other equipment, and then packages, etc. So with the help of that one, and with the help of PFDs and P&IDs and process data sheet, others will start doing their engineering. And then once they make the data sheets and they make the other calculations, then that will be converted into layout and other things. So these are the engineering workflows. Of course, I just said correctly in the beginning, the main role will be of the process engineers, and process engineer will have to develop PFDs and P&IDs, and with the help of that one the others will follow, like plot plan and piping will do the layout and their drawings, and then other studies and layouts will be done, and 3D modeling will be done, and isometrics will be developed, and then and the mechanical static engineers or stress engineers will be doing their jobs. Stress is nothing but it's a study for the critical lines. Here it will done. So after doing all these engine phases, then they will take the material takeoff, and then material takeoff will give them the all the list of the material required at the different stages by different disciplines, and then that will be procured. And of course that is all depending upon the PFDs and PNIDs. So PFD and PNIDs plays a big role here. That is our focus. Then we'll see what are those items. And if you talk about 3D modeling, of course this will be again developed with the PNIDs only, and plot plan and PMS. PMS will give the line specifications. So the first model will be done in the first phase 30%, and the second phase of the 3D model will be 60%, and the third phase will be the 90%, which will have complete major lines and smaller lines, pipelines, and major cable routing to smaller cable routing. It will have minute details. In the beginning, we'll just make a broader equipment layout and other major equipments in the 30%. Then it will carry forward with some sort of inputs, more inputs, and then 60% will develop. So like that, these are the different stages of 3D modeling. And of course it can be done in a modular way or in skid phase. And again, these are the 3D modeling phases by piping general arrangement drawings will be developed based on this one. And this will be the three phases, and finally we will be making the piping general arrangement drawings, and then it will be issued for approval. And then once it is issued, then finally it is converted into issued for construction. So if you talk about the process piping integrated mechanical engineering phases, as I said earlier, process flow schematical process flow diagrams will be developed, and P&IDs will be developed, and then further it will be given so that the piping and mechanical will start plot plan, piping routing, and similarly process studies will be done parallelly. Process engineering workflows will be done, process data sheet. So the oranges will be done by the process engineers if you see the color in the top line. So PFDs, process heat studies and calculations, and heat mass balance, and all those studies will be done by them. Feasibility studies by the process, and process data sheets will be prepared by them, and it will be given to other disciplines. And then the other disciplines will be making their requisitions, their RFQs they will make, and they will make the data sheet, and they will make the RFQ. They'll float. It will be given to the procurement department. Procurement will float those documents to the market, and then they will get the offers, and those offers will be evaluated, and technical bid evaluation will be done. And commercially, if it is okay, then the PO will be issued. And once the PO is issued, then vendor drawings will be received, and vendor drawings will be reviewed and approved for fabrication, and then factory acceptance test will be done, and the delivery date. So these are the green will be done by the different disciplines, piping instrumentation, piping, and other things. And if you talk about the specific piping in the blue, plot plan will be done by them, piping routing will be done by them, and then first cut MTO will be taken out, then piping general arrangement drawings will be done, and then with that one they can do the second cut of the MTO that will be more enhanced. And then piping flexibility study and loading, and then pipe support drawings. Of course pipe support drawings will be done based on the stress analysis by the specialist engineers for the critical lines. Then isometric drawings will be issued, and then time list and other final MTO will be extracted there. And during this phase they will be, of course, parallelly they're making specification and standards, and then MRs, and then MTO, first MTO, and then vendor offers will be evaluated, technical bid evaluation, and the second MTO will be given it to them, and then it will be revised at this second and third stage, final MTO. Then the PO for the piping material will be issued. So these are the different phases, just example what process engineer will be doing in these phases of engineering, what piping engineer will be doing, and the mechanical engineer's responsibilities. If we talk about broadly by piping and pipeline, so piping will be a complete piping engineering, and pipeline generally across country, like longer, for example, one place to another place, and then those will have different philosophies. So those will be both of them will be having piping layout and other things. Of course, they will be doing 3D modeling and design calculations, and then technical specification they will making, and they will be making the piping material specification or wall material specification, PMS or VMS. This plays a big role because the process has already identified that one, the particular fluid will be flowing through that pipeline. Then that will be taken as an input by the piping engineer, and the piping class will decide that what should be the material and what should be the flange rating, what should be the rating of that particular to withstand the pressure and flow and temperature. So any fluid which is flowing inside a pipeline will have different characteristics, different physical variables, and those are very critical, which needs to be taken care of when you are making a pipe, and when you are procuring a pipe and installing that pipe and allowing the fluid to pass it. So that material of that particular pipe should be in line with the fluid which has the physical properties, and that physical properties should not affect our pipeline. So the pipeline will be designed based on the fluid line list, and then of course routing will be done as per the plot plan, and a survey layout will be done. The piping alignment sheets will be done by, and it is more or less applicable for the pipelines basically. And of course for all these things we need to have material acquisition, technical bid evaluations, and vendor flow follow-ups. And when we are doing all these things, we are doing actually development of detailed piping drawing, including isometric, general arrangement drawings, bill of material, MTOs, and deciding the quantities required to procure or required to do the installation. And of course, this will be done with stress analysis and final reports. A mechanical engineer, static engineer, or rotating engineer will be making the equipment data sheet or vessel data sheet and specification. For example, heat transfer equipment, heat exchangers, fire heaters, and other vessels, pressure vessels. Pressure vessels, ASME Section 8, Division 1 and 2, API 650 and 620, they will have to follow this one. So this is the international standard. So everybody will have their own standard. I'm just giving one example over here, so that a static engineer will have to take care, because these are the critical pressure vessels. Pressure vessels actually nothing but a bomb which carries a fluid with certain pressure, and that pressure with rise of temperature will have different characteristics. It can withstand, it cannot withstand. So when you are designing, when you are making a pressure vessel, then you should be careful with all those parameters. So these are applicable, pressure vessels are applicable for the columns, vessels, bullets, tanks, and all those pressure vessels. And then of course this will be converted into fabrications once it is calculated, and the data sheets are being prepared perfectly, then fabrication can be done. And of course the required bill of quantities or MTOs can be extracted from there. And these are all depends upon the mechanical data sheets, and of course material acquisition, technical bid evaluations, all these are the part of that their engineering also. And then we talk about the civil engineering or structural engineering. So a civil engineer will be doing parallelly their engineering. So they will be taking the plot plan, and they will start making their structural general alignment drawing. They will do their stress, their static load calculations. They will get the loads for the pipe rack or steel structures. From piping they will load, they will take the load from electrical cable rail loads, and then they will get the load from instrumentation people. So civil architecture layouts for the control rooms and other buildings, substations, they will take the information from the instrumentation and electrical people. They will make the buildings, they will make the roads, they'll make the trenches, they will make the pipe racks based on that one, and they will do the blast design of the buildings. In case some places the control rooms will should be a blast proof, so these are the critical buildings which needs to be taken care separately. So they will be doing different type of engineering, special engineering for that one, and then structural calculations will be done, analysis will be done. The structural steel jacketing, mooring, and all those loading equipment will be done by them. Lifting analysis and calculations will be done, so that once when the equipment or skid will be made and then transported, then lifting analysis needs to be done carefully, so that the crane and all the other things, lifting, handling, material handling, will be taken care. And then of course bill of quantities and other things, bar bending schedule will be done by them, and structural detail drawings and shop fabrication drawing. So you can see the pictures here, the pipe racks and other skid just we have shown here. Once we go to process and health and safety. Actually, these are the two different the team of engineers working. And of course the simulation or study report will be done by the process engineer, and then hydraulic calculations will be done, equipment sizing calculations will be done by them, then heat mass balance and all those things calculations, and those things once it is done, then they will be developing the process flow diagrams and P&IDs. So here you can see where does the PFDs and P&IDs, which is our topic, will go next stage. So why I wanted to draw your attention into all these phases, because you should know where the PFDs and P&IDs stand in the total EPC aspect. So this is the place where you will come across the term P&IDs. So and of course, different calculations will be done and data sheets will be done by the process in process data sheets and will be given to different teams. And the line sizing calculations, like I just said, the different fluids will have different characteristics and their temperature and design pressure, and then viscosity, density matters a lot. And heat exchangers and all those will be differently handled, and boilers and all those things, and pumps which are rotating equipment, those will be dealt separately, and their sizing and selection will be done separately here. So that the process will engineer will have to give this to the static engineer or rotating engineers. Firefighting will be done by HSC engineers, and then of course the control wall sizing calculation, flow coefficient wall, and the thermal safety wall, and then process safety wall data sheets will be prepared by process engineer, or sometimes by instrumentation engineer. And there are different studies will be done by HSC engineers. Here just few examples: hazardous operability, hazard identification, hazard, and safety integrity level, SIL study level. And of course QRA and other disperse analysis and noise analysis and everything will be done by these people, and based on that one, HSC will be doing their separate engineering, and then like hydrant and all those things, and foam, for example, if a tank catches fire and how it should be mitigated, if any loading gantry is there, and how a fire can happen over there with the type of fluid. For example, if it is hydrocarbon, if it is petrol or diesel, then how it catches, and then what type of detectors to be used, and whether it should be flame detector or gas detectors, which type of toxic gas detector, or what are those things will be decided by HSC engineer. So these are the few photographs of P&IDs, which we will deal it separately. And of course, when talk about the engineering done by electrical and instrumentation engineers, so electrical engineer will be making the load list and power balance. They will do an SLDs. They will prepare single line diagram. They will make the data sheet for their equipment from what their motors, and they will make the data sheet for their motors and other things. And of course, they'll be making the cable schedule, and instrumentation will also make the instrument index, IO list based on the P&IDs, and they'll make the cable schedule. Both of these teams will make the cable schedule, instrumentation cable schedule separate and electrical cable schedule separate. And there both these teams will have their own layouts and installation details. And of course instrumentation engineers will make the hookup diagrams, so that the pressure transmitter or flow transmitter, how it should be hooked up, and the loop diagrams will be made, so that the construction engineer can do the wiring at site, and JB termination will also help them in wiring and cable pulling and cable termination. And of course substation will be done by electrical engineer, and control room design will be monitored by instrumentation engineers. And of course these two, like control will be designed by civil, but electrical and instrumentation will have to give the input, and they have to have their input required, and so that these buildings can be designed perfectly as per their requirement. For example, if UPS room is not adequate to accommodate a UPS panel and a battery separately, then that fails. So finally they will be issuing as built drawings. And of course space smart plant instrumentation is software, and electrical smart plant will be used for there. And of course here Instrucal also will be used by instrumentation people, that will be separate, we will talk. And then if you talk about instrumentation engineering, index IOLs data sheet they will be preparing, and then hookup loop diagrams. I will just go through quickly: cable schedule, junction boxes schedule, and these are all the drawings which will be helping for the construction people. And logic diagram will be for the DCS or PLC engineer, so that they can build their logic in the softwares, in the SCADA logic, and all in the SCADA graphics will be made. And the cause and effect will be the input for these things. by the process. So process engineer will make process flow diagram, P&IDs, and cause and effect diagram. That will be an input for instrumentation engineers, and of course finally the MTO will be floated. And here if you talk about instrumentation engineers, their activity IO list, detailed IO list will be prepared once the P&IDs and heat mass balance and other drawings are completed and the cause and effect are done. Then the instrument index and other IO list can be further done. To typical P&IDs and process flow diagram, we will see P&ID separately, instrumentation index and other things will be done. Here instrument index will be a detailed drawing, a document which will be prepared after receipt of P&IDs. So it will have instrument index, the fluid which will be as per the line list and description and the type of the instrument, and then line number which will be made by the process engineer based on the fluid characteristics and P&ID number, of course, and other things here instrumentation details like range and other things will have. IO list will also be prepared by instrumentation engineer based on the P&IDs, and this will give different type of inputs, like it can be a digital input, it can be digital output, or it can be an analog input or analog output. So these are the different diagrams, and of course loop diagrams which will start from the field to the control room and the final SCADA screen. So this will give a clear picture of complete one loop. It can be an open loop or closed loop. So this is an introduction session. So why I'm talking about all these things in quickly, because so that once we go ahead with our detailed program, when you opt our detailed program, then definitely each deliverable of each discipline we can talk separately. So this I'm giving you just an overview of this one. Hookup diagrams will be useful for the construction engineer or instrumentation fitters to go to the site and then to hook up an instrument, for example, DP flow transmitter or pressure transmitter. So control room design will be in this fashion. So these are the actually civil engineer's job, but should be looked after by instrumentation people. They may ask the required rooms or halls for their purpose, and UPS for example here, and then like cabinet layout and control room where the operators will be sitting, there should be a separate room. So all these can be monitored by instrumentation engineers given as an input to the civil engineers. Here of course the uh, static we will have a separate drawing so that we can monitor those things, what are the static vessels will have the instrumentation. And of course these are the loop layouts which will be helpful for an engineer to locate an equipment or instrument or electrical equipment at the site where it is located. This will give the clear picture in the overall plot plan with all the pipe racks, all cable routes, electrical routes, and electrical and instrumentation routes, and the location of instrument or location of the control room, location of the instrument. And of course cable schedule, this will be for instrumentation as well as for the electrical separately, and JB schedule for both of them. And these are the cause and effect diagram which will be prepared by process engineers, and that will be an input to instrumentation engineers with the cause and effect chart, where the process engineer will design which will define the causes. For example, vessel is there where in that vessel the pressure is increasing, the pressure switch is there, pressure transmitter is there, PSH in the if the high pressure increases, then what is the consequence and what should be the action, what should be the effect. The cause is pressure alarm high or pressure switching high, and the effect will be on a particular wall to close or open, or a drive or motor to be stopped or started. So based on that one, a logic diagram will be prepared by the instrumentation engineer. So this will have the basic logic, like function block diagrams. And data sheets, of course, as I said, will be prepared by instrumentation engineers based on the process data sheets, which will be an input to them by process engineer. And if you see the pressure transmitter here, we can see the basic general descriptions and then process condition. So here, if you see the process conditions are given by the process engineers. here the fluid characteristics and pressure and temperature and viscosity, density, design pressure and temperature, and the next the temperature, the transmitter details will be there, and the element, the sensor details are over here. So workflow, we've already seen this one. I'll just go through quickly, and this is the project schedule what I was talking in the beginning. A project engineer, a scheduler, a planner will make this one, and it will be monitored by project control department. So project control will be monitoring the entire phases of the project. If it is not monitored, otherwise it will go out of the control. And for example, a project is to be is scheduled for 12 months, then it should finish within 1 year. If it is scheduled for 1 year, it should be finished in 1 year, or 12 months. So each month or each week, what are the different phases? So engineering phase, procurement phase, construction phase, all these phases will be monitored, and this will be defined, and there will be a link. Like for example, until unless you get the process data sheet, you cannot go ahead with your instrument data sheet. If you don't have the P&IDs or plot plan, you cannot go ahead with your control room design or your substation design. Civil engineers cannot go ahead. Or layout of a pipe rack or layout of a cable tray for instrumentation and electrical cannot go ahead without the plot plan. So these are the sequential engineering. So generally, this should be followed religiously. But nowadays, I have observed that people are skipping this one. But it is advisable not to skip this schedule. And this is a sequential schedule. This you cannot overlap. You can do some sort of engineering parallelly, but you have to have sequential engineering. So first phase, that is the reason we call it engineering phase, and then the second phase, the procurement stage, and the third phase is the construction, and then the fourth phase we can say the commissioning stage, and the final stage is the handover. So these are the work front concepts. So every phases should have work fronts. For example, for the work front of any engineering phase is the PFDs and P&IDs, and without those things, the other engineers cannot go ahead. Similarly, a construction engineer requires issued for construction drawings. Until unless IFC's drawings, for example, IFC piping isometrics are not given to them, they cannot go ahead with their. So these are the work front for their this one. So every stage requires work fronts. So those work fronts needs to be followed, and those depends upon others. So here we can say that when it is a concept of internal customers. So one engineer is a customer to other engineer, and other engineer can be said as client to another engineer. So engineering you cannot do alone, and it is interdependency, and that is why we call it ITC checking and all those things. If I am a civil engineer, if I am going to make a substation without consulting anybody else, without consulting the plot plan, without consulting the pipeline engineer who has developed the plot plan, or without consulting the electrical engineer who will be making their plant cabinets and all those MCCs which will be put into that particular substation, then it is not possible. So everything is required by others, and others should follow. So piping isometrics here, for example, is the IFC drawings, which is the work front for other disciplines. So here part of construction, like as I said, these are all engineering work packages which are interdependent, and construction work packages will be made once each phases are done. So path of construction and engineering work packages and construction work packages are different packages, and then finally field installation work package will be done. So if you see, these are the sequential steps. So that's what actually it is, that one. So just be innovative and be triggered with the growth. Now I'll come back to other topic. Yeah. I hope it is visible.
Yes.
Yeah, okay. So this is the process flow diagram and P&IDs. Now we'll talk about that one. So as you said correctly, why means in detail we have seen that one. In each phases, all these engineers will be working, and those engineers are dependent. In means we can say that interdependent, to be precise. But all these engineers are depending on the process or chemical engineers. Chemical engineers are the engineers those who will start first. So once a process engineer takes the project, they have to see the feasibility whether the project can be executed or not. So for making that one, they have to make the process flow diagram or block flow diagram. So they will see what sort of process has to be there. For example, if it is LNG or LPG or a wellhead, like wellhead engineering, or maybe an offsite and an offshore or onshore project. So they have to see what sort of project and what sort of product will be handled, what sort of product will be extracted, and it will be delivered, and where it will be delivered. So the source of the particular fluid and where from it is extracted, and finally it is processed in the middle, and then finally it will be delivered. So these are the three aspects they have to see: from where it is extracted, and how it is processed, and then how and where it is delivered. So based on that one, they will be making the process flow diagram. And once the process flow diagram is made, then they will be developing the next stage piping and instrumentation diagram, P&IDs. So this is our agenda today for this one. So process flow diagram, it is nothing but a graphical representation that illustrates the sequence of operation. I said sequence of operation means starting from where and ending where. So major equipment, it will not have detail actually. This is a block diagram, so that's why we call block flow diagram also sometimes. And relationship with other complex processes. So the major equipment will be here. It will not deal with, for example, a drain line. It will not talk about the drain line. It will talk about the major equipment. So it uses cross industry like chemical, business operations. So PFDs uses symbols and connectors to visualize data flow, identify bottlenecks, and improve communication, making them essential for process design, documentation, and optimization. So this is nothing but actually a basic study done by the process engineer, put forward into the flow diagram, which can be of any other shape, any shape. Not necessary that it can be in one shape, but this is the block flow diagram which will give the initial skeleton, we can say, to anybody, even to the client, to other engineers. So this should be developed by them, this should be explained by them to all other engineers. So here it is nothing but, as I said, it is a visual representation of the steps of the equipment involved into that one, and what are the relationships. How, for example, if it is a vessel, if it is a boiler, what material it is, what fluid it is handling, what is the output, whether steam is coming out of that one, what is the characteristic of the step, if it is heat exchanger, what sort of heat exchanger it is, and if it is a tank, what sort of tank, what shape of the tank, and all those things it will have. And of course this will be done by chemical engineers, and it will show inputs and outputs, and with the complex systems it will be going through. Here how it looks like that one. So as I said, this will be developed by chemical engineers, we call them process engineers. So they will make process flow charts and flow sheets and block flow diagrams, schematic flow diagrams, and macro, what it may be, it can be of any shape. But these are the drawings which will be. So here if you see a process flow diagram, for example, here this is a crude oil, it is coming here, and these are the equipment which are handling it, and then here which is passing through this one, and then it is going to the one another equipment, and from here heat exchangers are there, and then it is pumped back to that one, and then it is pumped to another unit. So this is a simple flow diagram. Here another example you can see here, and here if you see, for example, here, sorry, I have to make it, I forgot to make it. Okay. Yeah, it is more clear here. So, for example, a crude oil is received and it will be pumped through a centrifugal pump to cold preheat train. So here it will be preheated, and it is nothing but a cold equipment, and how it will be handled and all those things they will know. And then here it will be having a device emulsifying, and then desalter is there, and then again it will be given to heat hot preheat train, and then from there it will be going to the crude furnace. So this will be a flow diagram, block flow diagram, which will be developed by process engineer, none other than them. And this should be understood by every discipline, because we are going to handle this one. For example, if you are an instrumentation engineer, you should know the process flow. If you don't know the process, and you don't know the material or fluid which we are going to handle, then you can do mistake. Similarly, if it is a mechanical or piping engineer, if it is a piping engineer, then they should know what is the fluid being handled by their pipelines. So they should know the characteristics of the particular fluid, what sort of temperature, pressure, and design pressure. So based on that one, they can design their pipeline, they can make their flanges, what sort of flanges are to be used, so that it can withstand to that pressure and temperature. So we can say class 150 pound rating or class 300 pound rating. If you join our courses, then definitely you will know what are those terms. So I'm just going through quickly. Now this is another example of a block flow diagram. So here, if you see here, this is the accumulator. Here we are measuring the pressure, and we are having pressure control, and with that one we are controlling the gas to flare. So this is the control valve, this is the pressure in the vessels. The pressure increases, then I have to open the valve so that the gas to flare can be increase more. So this is a closed loop, which is an example of a particular flow diagram. So flow diagram will not show much on into this one, but definitely it will define what is the pressure, what is the temperature, basic parameters, and basic and critical controls. It will not talk about a pressure gauge or small instrument, small walls, or other things, but it will talk about only the major lines, major equipment, major pumps or major vessels, heat exchanger or accumulator or pump, or maybe a cabin, a tank or vessel or bullet or sphere. And it will talk about a major parameter control. For example, here pressure is being measured and pressure is controlled. Maybe there may be level also, which is just for measurement purpose. For example, here the level is measured, but again it is controlling here. So this level is being control, means level transmitter is controlling the level wall of this particular pump outlet. So this is defined by them. And once it is defined by the process engineer, then it has to be followed by everybody. So every discipline engineer, pipeline will make their equipment, their pipeline engineering based on this one only. And for example, a static engineer will design this vessel based on the ASME standard I said in the beginning, ASME section 8. So these vessels, they will make the data sheet based on the process data sheet, vessel data sheet they will be preparing, and then instrumentation engineer will make the data sheet for this pressure transmitter based on the process data sheet given by the process. So process plays a key role in the beginning. So when you talk about the PFDs to P&IDs, so as I said in the beginning, the block flow diagram or schematic flow diagrams are nothing but it will give the overall idea of a plant or equipment, and it will have an overview only. It is having less details, but critical controls and critical parameters will be defined over there. Of course, I have not shown that example, but in that example, it should have been a pressure or temperature. It will generally mentioned over there. So those are the critical lines, critical vessels, critical lines. So important lines, pipelines, important vessels, important pumps and other things, and important controls of the parameters. That is a flow diagram. So once the flow diagram is finalized with the arrow direction going from where to where, then the next stage is to develop the P&IDs. The P&IDs, piping and instrumentation diagrams, are more technical, more details actually. This will be used by other engineers, piping and instrumentation and other things. So P&IDs is nothing but a detailed schematic drawing of process plant that shows the physical arrangement of equipment. Remember, this is a broader picture of the P&IDs, of the PFDs. PFD, for example, it is shown, everything shown in the one page. But P&IDs, once we go, it can go up to 10 or 15 or sometimes 50 to 60 pages, and it will have interconnected lines. For example, if a tank is there, in one page you can show only one tank because it has got different lines, different incoming lines, different, for example, nitrogen line is coming, where maybe the main line is coming, maybe the purging line is coming, maybe the drain line is shown over there, like that. So this in the PFD one, many equipment are shown in one page only, but here it can be shown only on one page. So it will have interconnection lines, because to connect other equipment or other controls, so there will be interconnection lines for the pipelines and interconnection lines for the instrumentation control, though it can be hard or soft. So it includes a standard set of symbols to represent the various components. So when you make the P&IDs, you cannot make a, a vessel as you decide or as you wish. There are different guidelines for the vessels to be represented. There are guidelines for the transmitters or instruments to be represented. There are guidelines for the different type of walls to be shown, like gate wall to be shown in different fashion, or a control wall should be shown in different fashion, or maybe a ball wall should be shown in different fashion. So all these things will have a different standards. You should have a guideline for that one. We will follow one ISS standard that I will come on that one. So I'll come back on that one. Now, if we talk about the key elements of the PNID, of course, the pipelines and piping lines, major lines, minor lines, bigger lines, smaller lines, and different thicknesses, different line sizes, all those things, and different line list. And line list will give the complete materials what fluid it's carrying. Equipment, different equipment can be there. It can be pump, it can be vessel, it can be heat exchanger, it can be a cooler, it can be compressor, it can be tank, it can be bullet, it can be sphere. And different walls, I said, it can be gate, globe, check wall, butterfly, control walls, on off walls, many type of walls, automatic or manual walls. Instrumentation like pressure transmitter, temperature level transmitters, and control walls, all those things will be shown in different fashion. And of course control loops will be there, and how it is connected. Pressure transmitter is controlling the pressure wall, or level transmitter is controlling the level wall, or flow transmitter controlling the flow wall, and can be a simple control, it can be a cascade control. All those control loops will be shown in their different hard and soft lines. These are the lines which I'll show you a standard for those, all these equipments and walls, how it should be shown. Safety features will be there, critical safety devices like pressure safety wall, relief wall, rupture devices, and other things will have their own symbologies. And of course, the flow direction will also be there. That is a major thing. Like for example, if we have a vessel here, then this vessel is having, for example, a pressure transmitter over here. This is the vessel, and the pressure transmitter, pressure control, and then pressure valve, which is controlling a line which is vapor outlet. So vessel is having a three-phase inlet fluid coming here, and a vapor outlet line is going. So this vessel may develop certain pressure. That pressure has to be monitored, and that monitoring instrument is pressure transmitter. Pressure transmitter is having a pressure control which is inside the PLC or DCS, and this is a DCS symbology, this is a field instrument, this is a field instrument. I'll show you international standard ISS standard S5.1, which shows all these guidelines, what are these symbols and how it should be shown. This is a safety wall. I am telling you because I'm having experience, but how will you know that one? I'll show that standard. And for example, here this is the flange, and these are the flanges for the level transmitter, and then this is the two lines and differential pressure transmitter actually, and level transmit, that is nothing but a level transmitter and level transmitter. This is a dotted line. I'll show you what is the significance of this one, and then this is the significance of the hard output going to the level control wall. So basically, this is the pressure wall, this is the level control wall, and these are the ball walls, these are the gate walls, and all those things. How will you come to know? And these are the spectacle blinds, and these are the breakers, and then all those things. How will you come to know? I'll show you the symbologies. So there is a standard actually, ANSI or ISA S5.1. You can say instrumentation symbols and identification. Before coming to this table, I'll just go to the basic symbols. Yeah. For example, a P&ID shows a symbol like this, then this is DCS symbol, and it is shade display and primary choice, and if it is discrete or computer symbol hexagon, and if it is alternate choice or sys, if it is safety PLC, or if it is DCS, if it is line means it is accessible, and it is also accessible, but it is ESD or safety PLC, this is basic PLC or DCS, and it is a computer software nowadays, it is absolute. And if it is dotted means it is located in the back of this one or not visible on the front panel. So these are the different symbologies, and this is for example a lamp, pilot lamp, and here for example a measuring symbol. If it is a circle in the PNID, and if it is second E means PE pressure element, TE temperature element, and first letter is T is temperature, and the second letter is temperature transmitter. So if you want to see that one, what are those things, we can just go here. This is the identification. If I say temperature transmitter has to be written in the PNID, for example, just show you one PNID. Just water I will just take to drink. Yeah. For example, in this line, we are having a PT written 304 and T 304. So how do I understand that P stands for pressure, T stands for temperature, or T stands for temperature, and this T, first T is temperature, second T is temperature transmitter. So here that will be first letter, for example TT, first letter temperature, first letter succeeding letter temperature, and the second letter is transmit. So like that, this will help you in identifying the codings or identification of the instrument shown on the P&IDs. And these are the symbols which are shown here. For example, this PI 3 for pressure indication is shown on the DCS. So this symbol is shown over here. Yeah. This is shade display, primary choice or basic process control system located in or front of control. So this is nothing but a DCS symbol shown on the HMI graphic. So with the help of this one, you will understand. So this is a standard which is governing the symbology of instruments and other equipment shown on this one. For example, this is the safety wall, pressure safety wall. This is a symbol, and this is the line number. And these are the, for example, line number 16-inch PRL. This is the fluid, another line number, and this is the description of other coding. So all these things, when you join our detailed course, then you will learn how to read the P&ID in detail. If possible for me to cover everything over here,